Hello, my name is Humera Ansari, and I'm a final year chemical engineering PhD student, and my research is focused on carbon storage in shales. Climate change is caused by an increased amount of anthropogenic carbon dioxide emissions, which have led to a rise in global temperatures as seen by this compelling image. We are progressively getting redder or warmer, and we need to figure out what to do with the CO2 we produce to avoid catastrophic damage to Earth. CO2 is mostly produced by fossil fuel production and usage. Carbon capture and storage, or CCS, one of the main ways to mitigate the effects of climate change, is a method of capturing that CO2 released from these sources and storing it long-term in the subsurface. And although CCS technology is available, there is still not a big enough push for industry to carry out CCS yet. But we will continue fossil fuel usage while we transition to a lower carbon economy. What if we could incentivize CCS by increasing production of the cleanest fossil fuel, natural gas? Shale gas is such a fuel. It's produced by fracking of shales, one of the most common rocks on Earth. But this often has poor efficiencies. Combining this with CO2 storage could lead to permanent sequestration of CO2 but also improved natural gas recovery. Proving feasibility of this process is the focus of my research. With my work, I try to answer four main questions. Firstly, how is gas stored in shales? Natural gas has existed in shales for many years, and it is stored in the form of adsorption. Imagine shale is like a sponge. It has small pores where gas can sit and interact with the surface. The pores are so small that gas molecules experience the pore wall significantly and get physically bonded to the surface. But how much space is there for gas? Essentially, how many pores and how much volume does my sponge or shale have? I measure this through cryogenic gas adsorption, and I obtain pore volume as a function of pore diameter. The main conclusion is that shales have pores that are nanometric in size, and there is significant pore space for gas to live, which is great because we have a lot of CO2 to store. Next, now that I know how much space I have, how much CO2 can I store at the conditions of the subsurface? The subsurface can be hot and very high in pressure because it is so deep. I measure adsorption of these conditions with both CO2 and methane, which is what natural gas is mainly composed of. The main conclusion is that CO2 absorbs up to 3 times more than methane. Finally, how do we engineer this process? I model this process by having 3 stages. Injection, where we inject CO2, soak, where we let the sponge or shale soak up the CO2, and production, where we produce as normal our natural gas. Some CO2 will also flow out, which we can recycle and re-inject. We observed that we can store up to half of the CO2 we inject and produce 70% more methane. In reality, we could design a multi-well system for the cycling injection process in which some wells are injecting, some wells are soaking, and some wells are producing so we don't experience time delays and operators are happy. Through this workflow, I have proven that carbon storage in shales is feasible and that there is both an economic and environmental benefit in implementing this process. Thank you very much.